Thank you very much. Hi, good evening, everybody. Great to be back in Lugano. I understand that I'm between you and your beers. I'm the last talk for today. I take it very seriously, and I'll try my best to kind of do it as quick as I can. I'm leading the cloud and AI activities at Mellanox, and I started a lot in around HPC, and it's kind of funny to see how things kind of circle back and how things are converging. Most of the talks today were about containers and machine learning. I'll cover some of this in this talk as well, with a focus on the networking side, mostly on the host side and virtualization. So modern data centers, modern data centers are evolving. The industry is moving towards more agile, programmable, on-demand, multi-tenancy environment. All of these nice things that allows people to easily consume resources from the network, from the cloud. And all of this enables really the growth that we see in clouds today. Most of these things, though, are implemented in software. They provide great value, but in most implementation, they come in expense of performance. And in many, for a long time, performance and cloud were kind of very distinct things. And even in the advanced cloud environment, you could see islands of high performance which kind of bypassed a lot of the programmability and multi-tenancy, and the major kind of standard cloud wasn't very high performance. On the contrary, it was very low performance, mostly because it was software implemented. And what we are trying to do is we're trying to bridge the gap, at least from the networking side, to provide both the flexibility, programmability, the software-defined everything, together with the highest performance that you guys especially are used to from the HPC, but not only HPC now needs it, but also the enterprise. The key for achieving high performance together with flexibility and agility is hardware acceleration or hardware offloads. Specifically for networking, we'll talk about how do we offload the networking, especially in the virtualized environment, in order to maintain both the flexibility, but at the same time, provide you the highest performance, lowest latency, highest message rate, and all the programmability that we need for today's environment. And this example here is showing, I think, the picture of how, cloud today treat networking. Sorry, I don't know, it doesn't work. It works, it moves packet, but very, very slowly. And what we're looking to do is we're looking to accelerate it significantly with hardware that is assigned to do networking in advanced modern data centers. So the talk will be around networking in data center, around clouds, mostly OpenStack, because this is kind of the open environment cloud that we have today. It doesn't mean that it cannot be implemented in other places. And then we'll talk a little bit about machine learning and a little bit about containers, a little bit of everything that people spoke today. So let's talk about what's important for cloud and how it is integrated with OpenStack. First and foremost is overlay network. In cloud, the notion of multi-tenancy is implemented typically with overlay network. Overlay network are the elements that enable us to do multi-tenancy. And just if you're not aware of what is overlay network, it's basically tunneling technology. So we encapsulate the packets with another header and then send it to the other side. The other side remove that header, and by that provide kind of a virtualized network, as you can see here in this picture, where you see two different servers. They may be in a very different location, even in the world, and using technologies like VXLAN, NVGRE, Genève, NSH, there's MPLS over GRE. There's a lot of different technologies to encapsulate the packet. Those VMs with the same colors on the different side see themselves as if they're on the same network. They're not aware that they're in the two different sides of the data center. So that allows us to do all this virtualized domain, virtualized network, but there's a caveat here. There's a challenge with the new packet format. Most of the network adapters are not aware of those new headers, and all the stateless offloads that vendors like Mellanox and others are implemented are kind of failing to recognize the packets. And therefore, all the checksum offload and all the RSS, the receive side scaling, a lot of the offloads are broken. And you can see the impact in this chart here on the right-hand side, where basically the performance, this is a 40 gig example, drops about 50%, by half. Not only that, the CPU load that is handling the packet processing is jumping about 3x to 4x. This is because the offload is broken, and that kind of breaks the whole concept of SDN, software-defined networking. Because if you get the flexibility, but you break the performance, you kind of didn't do much. The solution is, of course, to allow the hardware to be familiar with the new packet format and be able to restore those stateless offloads. And as you can see, this is the third bar on the right-hand side, once we enable the hardware offloads for overlay networks, for VXLAN in this example, then the performance resumed to the same level. So we can now do both overlay, but at the same time without losing performance. Also the CPU load that is handling the packet, you can see, is restoring itself to the same level as it was before. This is why these technologies are so important for the different SDN solutions out there. So people like VMware NSX or Nuage Networks, company from Nokia, Midekura, another, Contrail, all of them are using those capabilities because without it, basically it is not allowing them to utilize the environment properly. This is one side of overlay. The other side of overlay is the ability to do this encapsulation, decapsulation, this tunneling, implement that instead of in the CPU, implement it in the hardware. I'll talk about that later on in the slides. By the way, feel free to stop me at any time if you have any questions. Another important technology for virtualized environment, and right now I'll talk about virtualized environment, later on we'll talk about containers a little bit, is SRIV. SRIV, or Single Root I/O Virtualization, this is the full name, is a PCI technology that allows to virtualize PCI devices. It is if you look at what hypervisors are doing today, in most cases, they're kind of collecting all the requirements from the virtual machines. In this case, if we're looking at network, all the packets, and then implement some kind of virtual switch or virtual router in CPU. So the CPU or the hypervisor is implementing that, and eventually it's kind of coordinating the access to the NIC. This is how you do networking without SRIV. SRIV is looking at different direction, in a different direction. It takes the PCI device and basically slice it into virtual devices and allow each of the VM access to, this one works. I think it will be easier this way. Right, so the PCI device is being sliced, and each such slice, we call it virtual function, is being assigned or passed through to a VM. And by that, the VM can get basically bare metal performance out of this PCI. If we're talking about network adapter, then it will get bare performance from a PCI, from the network adapter. That is the most advanced way to connect devices into virtual machine. You don't see it a lot because in many places it is not fully integrated with the cloud solution. With OpenStack, Mellanox, and others in the community have been working to make it kind of a standard out-of-the-box solution, so you can use it today with basically 0 changes to OpenStack. Now, in addition to providing very high performance, it also exposes the PCI device, in our case, again, the NIC, to the virtual machine, and then every advanced technology or every advanced function that this device can do can be utilized by the VM. And this is very important, especially for HPC and machine learning workloads, because we're using a lot, many applications use RDMA, and that is the only way to expose RDMA to the guest operating system, so that you can run your MPI or you can run your machine learning framework in a transparent manner if it's in a bare metal environment or inside a virtual machine. And this is very helpful. Yeah?
So how much I have penalty from a latency point of view? And how much I can scale? How many VM I can scale?
The question is about penalty in terms of latency and scalability. So in terms of, and I'll talk only about the networking side, because there's some penalty also on the CPU side. On the networking side, the penalty is almost 0. In terms, obviously for HPC, when we measure nanoseconds, then there is a little bit more, but it's about 100 nanoseconds, give or take, which is very small. It's almost nothing. And in terms of scalability, it depends on the network adapter. For Mellanox adapters in our latest Connect X5, you can scale to about 250 virtual machines, virtual functions, basically. So it's pretty scalable. Yeah.
And can you prioritize different virtual functions over others? I mean,
From a quality of service perspective?
yeah. Virtual machine that
This is
better performance than the other?
This is what we call a great question. Yeah, now I lost both of them. Sorry about that. I guess my batteries are running. Yeah, that's the next slide. I will get to that in a minute, okay? There was another question just before I'll get there. No? Okay. All right. So that's a great question, both because it's just on time, and second because that was one of the challenges with SRIV. The reason that SRIV is not being massively used, or I should say is now starting to pick up, is because people were afraid about a lot of the services that they used to get from the virtual switch, from OVS or Linux Bridge or what have you. And there are some drawbacks for SRIV today, and we are closing the gap slowly. One of them was quality of service. In the SRIV use case, quality of service was implemented by the virtual switch. You could set rate limit, you could set min and maximum bandwidth, and so on. With SRIV, the question is, who is implementing it here? Now, I guess when I press this one, it takes, you know what, maybe I can, no, I'll stop using the laser here. So in our case, in Mellanox case, the NIC itself has very advanced quality of service mechanism that allows us to do very advanced things. One of the things we can do is the thing here you can see on the top. We can basically do rate limit and bandwidth guarantee per virtual function. So we can say this virtual machine will get, 100 megabyte, 100 megabit, whatever, minimum, and the maximum will be 1 gigabyte. We can even do traffic shaping, so we can guarantee that the traffic will go very smoothly. This is what we call packet pacing, very important for many applications. The nice thing is that we integrated it completely with OpenStack, so that in the same API that you set quality of service for the virtual switch, you will set the quality of service for a virtual function, for an SRIV-based VM. So you don't need any new tooling or scripts or anything like that. You just use the standard APIs that are defined right now in OpenStack for that. So this is one gap that is kind of closed in between SRIV. Another important gap. Yeah. I'm just replacing this. It doesn't work for me for some reason. Yeah. It depends how you define it. So basically, there are APIs that define the type of quality of service. It can be implemented. Depends just how you configure it. From the quality of service mechanisms that we have inside our NIC, you can do both fixed or best effort. So you can scale out or you can stay in the fixed. It depends what you want to achieve. Both can be done. Yeah, this is this rate limit. Yeah. Now the question was, sometimes you can say, I want to limit it, let's say for 1 gig, and that's it, even if there's extra. And in some cases you want to say, I want to limit to 1 gig, and if there's extra, just give it to the VM. So it depends on the, for example, you want to limit for 1 gig if, for example, you're a client provider and you charge for bandwidth. And then you don't want to give best effort. You want to give, strict. Depends. Another thing that was challenging for SRIV, and it still is, by the way, especially around OpenStack, is the high availability. The fact that, you want to have fault tolerance between your card and ports. So with OpenStack right now, it is still an open issue. We're working with the community. By the way, all of these things are upstream in the community, all the SRIV drivers and all the quality of service. So all of that was done together with the community. Mellanox is one of the large community members in that space. For high availability, though, we do have an interim solution where we can allow a transparent high availability mode until there will be a kind of a formal high availability mode. What do I mean by that? If you look at the VM, what we can do today is present a single virtual function, SRIV virtual function, but inside the NIC, we can kind of run bonding or lag, so that if one port fails, physical port fail on the NIC, data will transfer to the other link immediately. And we support here active-active, so you can do load balancing, and we can support active-passive, depends what you want to do. But basically, this is kind of a transparent high availability mode that allows you to maintain high availability without the need to be aware of that by the OpenStack layer itself. There are still some challenges with SRIV. One of them is about migration, live migration, that the community is working on right now. Right now, there is still no solution for live migration with SRIV that is formal by the OpenStack community. But I think that once that will be there, we'll have basically similar capabilities between para-virtualized or virt.io interfaces and SRIV interfaces. All right. So we talked about SRIV. I showed you earlier that with SRIV, the alternative is virtual switch that is running in the hypervisor. And each of them has its own kind of advantages. The virtual switch has all the flexibility and the programmability. So basically, all the SDN layer is implemented by, in most cases, by configuring the virtual switch. And SRIV has all the performance, but it bypasses the SDN layer. So when you run SRIV, you cannot run an SDN controller and configure per flow, approval, deny, and advanced programmability. And the question is, how can we converge them together? This is one question, and the other question is, how can we get virtual switch-like functionality with the high performance and offloads that the NIC can provide? The challenges of virtual switches, they're very helpful in terms of the system, but they're very challenging in terms of the ability to handle packet flow. If you look back at the very old switches, you would see that most of the old switches were implemented by some kind of a CPU when the link speed was very, very low. But as we moved ahead, all the logic of per packet handling, what we call the data path, was moved to a very specific ASICs, silicon. In virtualized environment, we are running the network, the data path in CPU, in the general purpose CPU, which is very, very challenging in terms of performance and in terms of the load that it puts on the x86 CPU. And that's the biggest problem of virtual switches or virtual routers. Basically, we get very, very low performance and very, very high CPU utilization. And when we look at what this data path include, it basically, especially if we look at more advanced data path, it is a pipeline of looking at doing classification for the packet, look at the packet, look at the different header, decide what flow is this packet belongs to, do something with that, and then maybe do another classification and do some action about it, and so forth, and eventually send the packet. If you're familiar with OpenFlow, this is kind of the concept that OVS, Open vSwitch, and others are doing today. What Mellanox did is basically implemented a data path engine inside the NIC. So inside the NIC itself, we have a component called eSwitch that can do hardware-based classification of the packet. There's very large tables, flow tables, that we can program them completely in software. And then there's action that we can do per packet. There's a very long list of actions that we can do. We can drop, we can allow, we can forward, we can mirror, we can encapsulate, decapsulate. All of this we can do in hardware. And basically, we can implement the data path in hardware. This allows us to do very advanced use cases, or different type of use cases. First, this technology is called accelerated switching and packet processing. It is a very long name, so we call it ASAP square, easier to remember, and it's also fast, so ASAP is easy to remember. And ASAP square allows us to move all the virtual networking that is done on the host to the NIC. Data path, not control plane. Control plane stays the same. Data path moved to the NIC, and you can see here just a few examples of use cases, because it's a family of use cases. We'll focus on this use case here, and I'll try to maybe show you some of the benefits that it can provide. So what do we see here? We see virtual machines that are connected with SRIV to the NIC, and the data plane is going directly from the NIC to the VM and back. It doesn't go to the hypervisor. But unlike standard SRIV, which this plane is completely bypassing the virtual switch, in this implementation, they are connected. How are they connected? In the control plane. So basically, the virtual switch is now aware of these virtual machines and basically program this advanced mechanism, hardware mechanism that we have. And then the data that travels now is impacted or governed by the virtual switch. So we can get the flexibility and the control with the performance of SRIV. So this is what we call the ASAP square direct. There's also ASAP square flex and application acceleration. We'll not get into that today. It will take too long. But just to give you, I kind of explained that earlier. This work was done together with the Linux community, OVS community, and OpenStack community, a lot of open source environment. We sat together with the Linux community to define how offloads are done in general in the Linux kernel. New concept came along called NetDev Representer. This is a net device that represents a virtual function. It is in the Linux kernel since kernel 4.13, some time now. I'll not go into all the details. I do want to show you kind of what is the advantages, or what can you achieve from that, and why I think it's interesting not only for enterprise and telcos and alike, but also for HPC. So first, if you look at what people are doing today, the alternative of running high-performance virtual switch is running the virtual switch over DPDK. So what they do is basically, we'll talk about DPDK in a minute, they bypass the kernel with DPDK and accelerate the virtual switch. And this benchmark, what we did is basically, we ran a VM that just doing forwarding over DPDK, so it will have the highest performance. And then the OVS here is also accelerated by DPDK. we push traffic from the traffic generator, in this case Exia, through the NIC all the way up, forward, and send back, and we measure how many packets can we do per second. And that's the highest performance in the industry today other than offloads, hardware offloads. On the other side, everything looks the same except that we use SRIV with OVS offload. So we control the NIC with OVS, and then data path go this way. The results are pretty interesting, I believe. When we look at only single flow with OVS, OVS over DPDK, we get to about 8 today, a little bit more with the updated OVS DPDK, about 10 million packets per second. Those are small packets. While with the offloads, we get over 60 million packets per second. So it's about 6x, let's say. The more interesting thing, I believe, is that to get to this number, we need to use about 4 CPU cores just to run this DPDK to get the packets and handle them. With the offload, we use 0 CPU. So not only that we get 8x more performance, we actually free up CPU for the application to take advantage of them. So this is the OVS offload. You'll hear a lot in the industry, people talking about the use of SmartNIC to do OVS offload or virtual switches offload. There is a lot of discussion about what's the right way to do offload. We believe that there's multiple ways to do offload. You can offload the data path. That's what we're showing here. But you can also offload the control plane. But for that, you need a kind of a NIC with a CPU. This option also applies, and there's reasons to use it. But in most cases, we believe this is a great solution to accelerate virtualized network. And by the way, you can also run RDMA on top of that. So it's not only for TCP, UDP. You can also run RDMA with these offloads capabilities. All right, let's move forward. Kind of lost track of time. I don't think I need to explain RDMA to this audience. Usually for the enterprise, RDMA is something that is new. You all know what RDMA is, all the benefits, all the applications that we can run with RDMA. In the cloud, in HPC cloud, obviously, you understand why you need RDMA. But in other clouds, people are now needing RDMA for 3 reasons. One is to accelerate application. HPC application, obviously, but also machine learning application and others. But there are 2 other reasons to run RDMA. One is to accelerate the cloud infrastructure itself, mostly around VM migration or around using the communication pattern inside the cloud, typically using some kind of message queue that can be accelerated with RDMA. And the last piece is the storage element itself. So storage is a great partner for RDMA. RDMA can accelerate storage. And as you know, we can accelerate multiple types of storage. We already integrated ISER, which is iSCSI over RDMA with OpenStack. So with any deployments of OpenStack, you can use ISER, which is iSCSI over RDMA. With that, in a pretty straightforward, you can get very high performance, especially with flash-based storage like NVMEs and the like. Without any modification, you can get a very fast storage. We are now working on driving NVMe over Fabrics integration with OpenStack so that you can take advantage of NVMe over Fabrics and provision that natively with OpenStack. That will be in the next OpenStack release, not in Queens that is coming now, but the one after.
How that's going to be implemented?
I'm sorry?
How that's going to be implemented in OpenStack?
So in OpenStack, I'm using this slide just as an example. In OpenStack, there are probably 2 main storage frameworks. The most important one is Cinder. Cinder is the block storage provisioning of OpenStack. It allows you to, it's an API that allows you to allocate and provision blocks into different VMs. For Cinder support iSCSI. To do ISO was pretty easy because all we had to do is just change the transport from TCP to RDMA. We are now working to enhance Cinder to take advantage of NVMe over Fabrics itself. So it will be through Cinder.
So Cinder will be just
Yes, yeah. It will be another type of protocol for Cinder. Now, there are other solutions, Swift for block storage, and Ceph is not OpenStack, but many use Ceph as well. There is a solution for Ceph over RDMA right now. It's being redesigned as we speak because we're going to enhance it significantly. But I'm not taking this as an example because just time. Okay. DPDK, I was kind of hesitating if to talk about DPDK. Is it interesting for anybody, DPDK here? All right, so I'll just go very quickly with that. DPDK is a set of libraries to allow acceleration of networking, which is not RDMA. RDMA is far better than DPDK, but in many cases, people already wrote their application to run over DPDK. It provides kernel bypass, mostly, but also a lot of other services to do better or to take advantage of the x86 in a better way. But we'll talk about the kernel bypass. If you compare that to RDMA, then obviously it's not. RDMA is faster. DPDK is just getting to about 140 million packets per second just now for 100 gig, which is almost line rate. RDMA did that on the first day of RDMA, of 100 gig. Nevertheless, that's an option to accelerate non-RDMA traffic in some cases. So, but we are getting very close to line rate. Another interesting case with DPDK for those who need it is the ability to provide secure RDMA. I'll talk about it a little bit more in the containers. Let's skip it. I don't think we have a lot of time. I think this is more interesting for this crowd. So OpenStack is very Ethernet-oriented. All the networking elements with OpenStack is IP, MACs, VLANs, VXLAN. This is what Neutron, the framework for networking in OpenStack, talks about. Mellanox understood that RDMA, InfiniBand, is also part of the community, and we did a porting to allow using OpenStack over an InfiniBand fabric. We did that in a transparent manner, meaning that when you provision a virtual machine, you provision it just like you do with Ethernet, but under the hood, the plugins that we provide can translate the Ethernet into InfiniBand and allows you to run intact in an InfiniBand or with InfiniBand fabric. This has been available for a long time, actually, now, since Havana release, which is probably 4 years ago. And we're seeing quite a lot of use cases of InfiniBand-based cloud out there. You're more than welcome to use it. It's open source, and you can deploy it today. Another interesting case, I think, for this crowd is bare metal provisioning. So one of the challenges that people face, especially when they go to HPC, is with the penalty of virtualization. All we talked now about bypassing the networking layer and providing bare metal performance is with the assumption that there's a hypervisor and this hypervisor is very slow and you need to bypass it. So we can get you a very good networking, but in the end, you're still running in a virtualized environment, and a virtualized environment has penalties, also from the CPU. And many customers don't want to have that. They want bare metal. But on the other hand, they do want the APIs of OpenStack and the ability to drive their data center from a softer level. And one of the solutions for that is bare metal provisioning. So OpenStack has this ironic framework that provide the ability to provision bare metal servers in the same way you provision virtual machines. It was designed actually for the deployment of OpenStack, but later on was enhanced to also be able to do bare metal provisioning itself. OpenStack, again, was designed for Ethernet, so the first kind of use case was Ethernet-based bare metal provisioning. We enhanced Ethernet bare metal provisioning to be able to also provide multi-tenancy with bare metal. So basically, you can run multi-tenant cloud with bare metal support, where the switches are basically controlling the access. And we also enhanced that to also be supported over InfiniBand. So you could have an InfiniBand network and provision servers through OpenStack in a programmable manner, and that will be done also with the multi-tenancy environment with isolation of P keys, partition keys. The way that we do it is, you can see here, what we have done is we developed this component to the Neutron agent called Mellanox SDN Assist, mechanism driver. That is simply a device or element that reflect all the changes in the Neutron database outside through a RESTful API. And then on the other side, we connect our Neo. Neo is a fabric management tool that later on just go and configure the switches as needed to match for the multi-tenancies configuration. Neo is a topology-aware element. Neutron is not. Neutron only aware of the virtualized environment. Neo is aware of the physical environment, and together they can provision the cloud as needed. Any questions? So I think I have another 15 minutes if I remember right. This is just kind of a grand scheme of where we are with OpenStack. Basically, we're accelerating different elements of the stacks, mostly Neutron, Cinder, and Nova. Those are the environments that Mellanox is playing and providing the network acceleration. We are supporting basically all OpenStack releases since Havana, which is a long time ago. Everything is upstream. We are supported with all the kind of key OpenStack distributions, mostly Red Hat and Canonical. Laurent has changed a little bit the mode of operation. And as I said, we support both InfiniBand and Ethernet clouds. Okay. I'll move forward, if you don't mind, talk a little bit about machine learning because we're running out of time. There was a lot of discussions here today about machine learning. I will, again, try to stay on the network side. This time I'm talking about the physical network rather than the neural network. It's kind of... so everybody spoke about it. I'll just go very quickly. Everybody understand that this is a disruptive technology, and we see very fast growth around this space. When you look at the size of the neural network, you understand how significant it is. If just in 2012, with AlexNet, mentioned it earlier, it was a very small kind of the first neural network model that actually been able to compete with human classification. Today, just actually not today, 2 years ago, we already grew the networks to about 350x. Those are huge, huge networks, and we believe that they will continue to grow. We believe that we're just in the beginning of this. Image recognition networks or models are the fastest growing, but also speech recognition is growing very quickly. And the challenge with, especially with the training side, is time. It's complex. It takes a lot of CPU. And there's two aspects here. One is the development of the neural network. Writing a neural network is not systematic, like writing a program. You write it, you run it, you change it, you run it, you change it, you run it, you change it, you run it. I have a friend that is a machine learning expert, and he loves his job because he writes, he run, he go to drink a beer, and he come back next day. So basically, you know, half of his day is completely wasted. Obviously, that's not acceptable because it takes a long time. In addition, in many cases, we need to do continuous training on new data. And if it takes you a day or two to build a new model and the changes are happening every day, that's not really converging. So we need to accelerate that, and we're accelerating that with distributed use cases. I will not cover that again. The model and data parallelism, I think, was covered here enough. I will, though, focus on data parallelism. Model parallelism, even though is happening, it happens mostly with smaller compute engines like FPGAs. So I'll skip that. We'll focus on data parallelism. In data parallelism, basically, if you look at the type of communication patterns that are created, they're very similar to HPC. Low latency, high bandwidth, this is what you need, collectives, all the good things that this community has been using since many, many years, and it's no surprise that the same advantages that provide HPC also provide advantages here, mostly RDMA, GPU-Direct, Sharp, and those kind of technologies really allow us to accelerate the networking, as well as, of course, advanced collectives implementation. So again, RDMA, I'll skip. GPU-Direct, for those of you that are not familiar, this is a technology that allows us to stream data in and out of the GPU faster. If in the past you had to go from the GPU memory to the system memory, and then from the system memory to the NIC, and there's a lot of extra copies, with GPU-Direct, we just can send and receive data directly. We've been working with NVIDIA for many years on that, and this is kind of standard practice in HPC today. Now it's also standard practice with machine learning. So if you look at all of the frameworks of machine learning today, all of them support RDMA, at least in one implementation, if not multiple. The most dominant framework today is TensorFlow out of Google, and that implementation, that framework by itself has, I guess, about 4 or 5 different implementations of RDMA, where kind of 2 are becoming standard. One of them is as part of the native implementation of TensorFlow, or distributed TensorFlow. This is a native RDMA implementation that initially was started with Yahoo, and today Mellanox is managing. And the other one is by work that was done by Uber, a framework called Choravot, which uses both MPI and nickel. I'll talk about nickel in a minute. And basically everybody that runs TensorFlow today in training use RDMA. Yeah, I'm not aware of anybody that doesn't. I'll show you why in a minute. But not only TensorFlow, also Caffe2, which is coming from Facebook, has implementation. Again, 2 different ones. One is over MPI directly. Another one is on a library called Glue that was developed by Facebook. Microsoft CNTK, NVIDIA Nickel. NVIDIA Nickel is kind of a different beast here. NVIDIA Nickel is not a machine learning framework, but it's a distribution framework for doing collectives in the most efficient way. They started doing collectives within the server, within a box between the GPUs. But when they moved out to a scale-out environment, they use RDMA to connect the different servers together. So basically, everybody that's doing out-of-the-box communication using RDMA. And why? Here's a reason. This is a benchmark that we did for TensorFlow. In our labs, we have 8 servers with 4 NVIDIA GPU each, so 32 GPUs. And what you can see here is we ran VGG16 and the Inception V3, and we ran it with TCP. This is this blue line here, with RDMA plus GPU-Direct, and this is the ideal scalability. This is the speed up that you get when you add more GPUs. And as you can see, when we use RDMA, we get a very nice speed up. But when we use RDMA and GPU-Direct, we even increase that and getting pretty close, at least with Inception, to the linear scalability. So if you're running TCP, especially with complex model, VGG16 is a very complex model, very heavy in terms of the number of weights. You barely scratch, speed up of, from 32 GPU, you get 5 out of 32, which is very, very bad in terms of efficiency. If you think that this setup is about $250,000, just, this 8 nodes, that if you get out only 5x or 6x out of 32, that's not very efficient. With GPU and with RDMA and GPU-Direct, we get to about 16x out of 32, which is much, much better, over 2x. So this is why people run RDMA all over the place. And in many cases, not Mellanox wrote this implementation, others did. The next phase that will be done in the community is getting also Sharp into the loop. Sharp, for those of you that are not familiar with, is a way to do even better collectives, this time inside the network itself. So instead of doing this, you've seen this drawing earlier today, instead of doing a parameter server or ring all reduce or those kind of techniques, we are kind of reducing within the fabric itself, within the switch fabric itself. The fan out and the fan in is much, much higher, and that will provide a significant improvement in performance. I'll skip all this. Okay. A lot of people talk about accelerating distributed training, but this is just one step of the data pipeline. If you look at the real production data pipeline, there's much, much more into it. Data comes from somewhere, need to go into storage, need to go into a big data framework, need to be sliced and diced and prepared for the machine learning. The machine learning typically is just the last phase, the really, really last phase. And if we are accelerating the machine learning, but we don't accelerate the whole thing, we kind of lost the battle, right? So what this phase that come before the machine learning side is the pre-processing or the ingest side. And what we really want to do is, we talked about accelerating the training. What we really want to do is we want to accelerate also the storage. And we want also to accelerate the big data framework, the Spark or the Hadoop or whatever you want. So basically, this whole pipeline will be accelerated. I'm short of time, so I'm going to skip this part. I need to finish in about 2 minutes. I do want to say, I do want to go and talk a little bit about Spark over RDMA, just in 2 words. I have 20 minutes? Okay. Sorry, guys. More time until you get your beer. So I'm going to take my time. All right, so let's... I'm sorry?
Oh, no, go ahead.
Okay. All right, so first about the storage. So we talked about ICER, iSCSI over RDMA, and NVMe over fabrics. Really, if you look today at any storage implementation, be it open source or commercial, you'll see that they're using RDMA or other acceleration one way or another. That includes company like EMC from one hand, the very, very large, all the way to the startups that are starting this year, and there are variety of them, Wake.io and E8 and all those guys. So the networking side is really, really covered. It's been accelerated. I'll keep talking about it here. I do want to talk a little bit about big data. Big data is a very important part of machine learning. It comes together, and this thing needs to run in the same cloud. So all the capabilities that we spoke about running in OpenStack or in general cloud applies here. What's really important for big data is the ability to move data fast and easy without any limitation from the servers and the storage. And here, what's really important is bandwidth. And this example can show you very nicely when we ran MapR on a storage that was flash-driven, or it was very limited by the network when we ran at about 10 gig. The execution time was, much higher. When we moved to 40 gig and later on 100 gig, because we all kind of opened up the bottleneck, just by moving to faster data pipes, we could reduce significantly by 3x the execution. Also, latency is very important for big data, not only bandwidth. Another great example is this fraud detection environment where you have that amount of time to do fraud detection in real time. It's about 700 milliseconds. And the networking part took about almost half of this time. When we moved to faster network, we could reduce significantly the network element, allowing much more time for the application algorithm itself to make a decision. Because this kind of 700 nanosecond or 750 millisecond is kind of our limit that they had. So this is even without RDMA. But when we get RDMA into the loop, then things get even more interesting. So one of the places we invested is with Spark. One of the common elements in most of the big data, and especially with Spark, is the MapReduce, where you have a bunch of mixed input, and you map it, so all the colors are kind of mapped together, and then you reduce it so you can process it later on. And usually you'll do that on multiple servers, and there's a lot of data exchange between the server. And this is a great place where RDMA can accelerate and make it much, much faster. And we implemented in the open source, so you can actually go and just download and use it. The benefits is significant when you're doing benchmarks like TerraSort. TerraSort is, well, it's pretty clear what it is, right? It's terabyte sorted out to sort a terabyte. When we're comparing standard Spark versus RDMA accelerated Spark, we can see a significant acceleration just by the fact that we are enabling much faster networking. And again, this all can run also in the cloud because we enable RDMA in the cloud. If you look at a real-life application, this is a customer of ours, and we just look at their application, you can see significant improvement, not in a benchmark, but in real environment. 20% in average is great saving by just enabling RDMA. There are many other frameworks. Hadoop, obviously, with the HDFS is one of the most popular one. We're working to accelerate that, and we'll continue and adding more acceleration to different frameworks. All right. Last part of the talk is containers. I'll not spend a lot of time. We had, I think, quite a lot here talks about containers. So I'll just want to tell you a little bit about what we are doing in that space. I'll skip all the intro. I think you've seen this multiple times today. What's the difference between virtual machine and containers? I think you all know. Let's focus a little bit about the networking. Just one point. Containers is very evolving. It's true that it started about 4 or 5 years ago. The industry is now behind it, and there's more and more and more power getting into it and focus, and it is evolving. I don't think we've seen the last. I don't think it's consolidated. There are a lot of different options. We're looking at the networking side, and we see a lot of movement in that space. Containers can be connected in all those options you see here. And I think you will see representation of them in different environment. Obviously, the virtual switches and Linux bridges and alike provides the flexibility, but have the same problem as we talked about before, the performance. There are some ways to connect the container directly to the NIC, MacVLAN and MacVLAN acceleration and these kind of things. So all of those can be seen, and basically what Mellanox is trying to do here is bring high performance into containers. Now, it is a little bit easier than virtual machine because with virtual machine, the VM is running isolated from the hypervisor, and we have to use different things like SRIV and stuff like that. With containers, it's a little bit easier because the container is in the same space as the Linux kernel, but at the same time, the challenge is how do we provision it as part of the solution. So, first and foremost, just the plain bandwidth and all the offloads, stateless offloads and stuff like that, that is obviously available natively. So you can use Dockers and you can use Kubernetes and you can use Singularity, whatever you'll get it because it's Ethernet. The question is, what's going on with the more advanced features? The kernel bypass, RDMA, which is really important. InfiniBand, for some people, DPDK is important. And the good news is that you can use it today, but you'll need to do some manual configuration. So you need to make sure that the different files are moved to the right containers and that C groups are configured correctly and namespaces are configured correctly. It can be done. We have made the changes to the Linux kernel to be able to use C groups for RDMA, so you can also track the resources of RDMA. But it is a lot of, not a lot, but it involves some manual configuration today. If you'll go to Mellanox website, you can find some how-tos and reference design on using RDMA to run in Dockers and other places, and also for application like machine learning to run in various containers. What we are now working is really to get it bolt into the different frameworks. So you could natively provision container through Kubernetes, and all those features will come naturally without any additional scripts and configuration. This is what we are doing today with the community. So those are this RDMA and SRIV and DPDK. And later on, we would like to even do more than that. We would like to accelerate the networking, mostly by two technologies. One of them is A²² Direct, as I mentioned earlier, basically offload the virtual switching and provide flexibility of SDN layer to containers, not only to virtual machines. And then the other thing is accelerating containers networking by providing direct connectivity to the NIC, similar to SRIV, but without SRIV. There's different naming for that in the industry today. There's no yet formal way to do that, and we are working with the Linux community to define it. And with that, I'm open for questions. Yes?
I had to take a course, sorry for just...
You just entered on the right time.
Could you go back one slide? Isn't this A², isn't it very low hanging fruit anyway? Plugin for Kubernetes and SC and then plugin for Docker,
Yes and no. So it's a little bit complicated. So it depends which A². A² is a family, as I said earlier, and the direct one basically involved connecting the container directly to the NIC and then offload the control plane. Connecting the container directly to the NIC requires something that we don't have today. I mean, we can have like VMDQ or something similar to that. Once we'll have that, then we can connect to it a representer and then do A² direct. For the flex, it can be done. I haven't spoken about the flex because of time, but it can be done today. But we think that it will be more interesting for direct than flex. So those two are basically kind of tied together. Once we have this, we can do that.
RDMA namespaces, I'm also a huge fan.
Yeah, so this we are working now. So so we need to talk. We are working, so it is doable today. We just need to close the CNI plugin. We're just working on that now. There is some considerations from our end because CNI is talking only about network devices. It doesn't talk about file descriptors, basically. And we need to assign file descriptor and slice it in. So there's some things that we need to sort out. Any other questions? Thank you.